Welcome to the lecture on graphics pipeline, which is a lecture within the series on computer graphics at KAUST. Today we will be talking about a different approach from ray tracing as an image order rendering, and we will be discussing another technique which is called object ordered rendering, or often also referred to as rasterization approach. Object object order rendering follows a different strategy than image order rendering, where we would start from a certain notion of an eye and shoot rays into the scene and see how these rays are intersecting with the scene. For object order rendering, we would do the opposite. We would iterate through the objects and somehow split them onto our screen so that those who will sort of be projected on the screen, they will be then illuminated and shaded accordingly. The central element of such an approach is called rasterization, which takes geometric primitives defined often through points that are connected into edges, into triangles and triangle meshes. These approximations of certain smooth surfaces are still represented by in continuous representation of triangles, and this continuous representation we will need to discretize, or vector representation we would need to discretize onto our set of pixels which constitute our screen. And this process is called rasterization. Before we perform the rasterization, there are certain stages which are referred to as pre-rasterization stages. And these pre-rasterization stages naturally would have to prepare the geometry somehow that is ready for rasterization. And as you might have already get your intuition right, in the pre-rasterization stage, we will perform the viewing transformation or the series of various viewing transformations and matrix multiplications which are related to placing the objects into the scene, so the modeling stage, so that our graphical elements or elements of the scene are already in the screen coordinates, because that's the moment when we can start the rasterization. Sometimes in this stage, or it has been the case in the past predominantly, in this stage the lighting was realized through per vertex shading. So each vertex was shaded, the illumination was calculated for the vertices, and then during the rasterization, also the shading can be distributed from the vertices onto the entire surface of each triangle these vertices correspond to or part of. After the rasterization, we have a set of fragments. So those are not yet pixels because each triangle will get some rasterized elements, and it is maybe not each triangle which gets finally rendered on an image. So for that, we would have a in the post-rasterization stage certain blending operation, which will then, in the simplest case, take only the closest fragment, which is to the viewing plane, which will then be forming the pixel color. Other way could be that several fragments are taken into consideration for coloring the pixel by taking into account, for example, the transparency, and these fragments will be blended together. These days, the shading is mostly not done in per vertex shading, and it's done on per fragment level. So all the illumination calculation has been moved to the later stage after the rasterization is done. So while before the per pre-rasterization stage was called transform and lighting stage, these days the lighting will no longer be realized at this stage, and in the most of the cases, all the lighting shading calculations will be done on the in the post-rasterization stage on the per fragment level. And this whole pipeline of object order rendering constituting from pre-rasterization stage, rasterization, and post-rasterization stage is called the graphics pipeline. That is the pipeline which is either implemented as a software pipeline or as a hardware pipeline directly implemented in a hardware of graphics processing units. So here we can see the pipeline once again, and the different stages are highlighted in blue, where also the individual results of these stages are shown. So at the beginning, we have a certain application where we prepare all the first of all, we have a certain scene, and also we have certain um, settings, states, which we would like to set up, how the rendering should be realized in particular. And once this all is set up, then so the graphics hardware is informed of the different switches and which programmable part is how should be acting. Then the data, the geometry, is sent down this pipeline along with information on the camera position and also about the lights, for example. And then through this vertex processing, which means that for every vertex, there is the same operation being performed, and each vertex is, for example, transformed. Once the vertices are in their world coordinates, they will be transformed with the viewing transformation, so that we get each vertex into the screen coordinates. By transforming the vertices but preserving their connectivity, we will be transforming the entire triangles and the objects which these triangles are forming. So after this stage, we have transformed the geometry, and this geometry not only contains the vertices as primitives, but on these vertices there could be additional information stored, so-called vertex attributes, such as, for example, texture coordinates, or, for example, per vertex normals, etc. Now, this stage, this vertex processing stage, is not a fixed processing pipeline, but it is something which is programmable. So there is something called a vertex shader, for example, which you as a programmer can code what should be happening in this vertex processing stage. The natural operations would be the transformation with the viewing matrices, but you can also think of something else or something additional which should be done in the per vertex stage. After this per vertex stage, the geometry is ready and prepared for rasterization. There are other stages which could be also, which are nowadays implemented in today's hardware. And these stages are, for example, could be emitting new geometry, for example, for some subdivision surfaces generation or applications like this. And once these are done, then the rasterization takes place. the rasterization is until now the only stage of a graphics pipeline which is not really programmable. Everything is sort of put in there. Maybe a few switches can influence the behavior of the rasterization, but there is no shader, rasterization shader, which we could sort of execute so that the rasterization would behave differently according to the program which we would specify. So the rasterization is more or less a hardwired process and results into fragments. From each graphical primitive, we will have several fragments, and these fragments will then be processed further. In the graphics processing stage, so-called graphic fragment shader, and in this fragment shader, we will be performing various operations. So each fragment will be rasterized, and attributes of the vertices will be distributed onto the triangle geometry, onto the position of each fragment. So we will have then interpolated values using barycentric coordinates, for example, which will give us certain information, such as, for example, a color, if we define a color on a per vertex, or a depth. So each vertex has a certain depth, and in between, on the side of the triangle, we would like to know what is the depth at a particular position. So these fragments also get an interpolated depth value. And all this information can be arbitrarily processed through a program so that at the end, we will end up with a certain color and depth of a fragment. And based on this information, including the alpha value potentially, we can perform a certain blending. In the standard scenario where things are rather opaque, the blending will result just in output of the most closest fragment to a to the to the pixel which it covers. We will be talking about the particulates of these programs on a separate lecture, which will be on graphics hardware. But on this lecture, we will be focusing on some conceptual aspects of what this rasterization does. So imagine that into the rasterization, we have already prepared all the graphics elements so that they are ready to be rasterized. So they are already in the screen coordinates. And once they are in the screen coordinates, then the rasterization turns colors corresponding pixels onto which these graphical elements or geometric elements are projected, and interpolates these vertex attributes across these primitives. And the desired output is the set of fragments for each primitive, and this fragment is associated with a certain position on the screen with a certain pixel, which it may or may not finally contribute to, depending on the interaction or properties of this pixel and other of this fragment and other fragments. So we will start with thinking about how a rasterization algorithms can be realized on line drawing. So imagine that the current scene which we will be dealing with will be a scene, maybe a triangular mesh, but we will be interested in wireframe models. So we will be only drawing lines, and we will not be filling the sides or the faces of the triangles with the respective color just yet. That we will talk about later, but for now, we will just make ourselves familiar with rasterization strategies and algorithms for line primitives first. So imagine that we have a certain 2 points in the scene, and we would like to draw a line between them. There are several algorithms which realize that, and one algorithm is called the midpoint algorithm, which is conceptually very simple and closely is related to the discussion which we already had about a definition of lines. Do you see this description of a line here? Fxy equals, and then we have some terms over here. It should look familiar to you because we had it already several times. We see here that we have certain description of a line, which is actually the implicit equation or implicit formulation, where we have the term A, B, and the term C here, which defines our line in 2 dimensions. So we do not have the z in this case, but the z is also not relevant in this case when we will have, even if we will have our points defined in 3 dimensions, we are interested in the drawing of these lines according to the x and y coordinates of the screen coordinates. So we have here this ax plus by plus c is the function value, and if this value is 0, then this point lies, the point defined by the coordinates x and y, lies on the plane, on the line. But what happens if this functional evaluation is not 0, but it's some other value? Well, then it will basically tell us that it is at some distance from our line. And it is assigned distance because it can be either above or below that line. So in this case, we will first be talking about a line drawing rasterization approach, which is slightly different, but analogously different for various orientations of line. We will explain the algorithm just based on lines which are of this. So here is P1, P2, and our lines will look either like this or, so let's say P3 here. So all lines which will be having this this behavior, this direction, and this will be within 45 degrees, will be drawn with the technique as I will describe in the next. All other orientations of lines can be done analogously by slightly changing the algorithm in a straightforward way. So in this case, our lines are characterized that they more run than rise. The vector, the horizontal vector of our, or component of our line vector is longer than the vertical one. And in such a case, we will use our implicit formulation of a line, and you can see we have all the information there available, and we would like to use it for the rasterization of this line. So how do we do it? We first start with the point P0, which is the first point on the line, and let's say the second one is P1. In this case, I started on previous slide with P1 and P2, but let's have the P0 and P1. Now, we first round the values of the P0 point, the starting point of the line, round up to the nearest pixel coordinates. So we would like to have some integer value, if you like, of both x and y dimension as a pixel coordinates where this line will start from. And then, so this is a first defined point. And then, remember, we will be going only within the lines which are defining 45 degrees, up to 45 degrees, between 0 to 45 degrees with the horizontal line. So what we will do is we will for sure need to draw another point at the position x plus 1. So this is our rounded x0, y0, rounded. And at this point, for the next one, we need to define, we know that we will be drawing another point on the line or pixel on the line, either on the same level, for sure it will be in this column, will be the next pixel which will be drawn, but the question is whether it is on the same level as the previous pixel or in the next level, one above. So this is a question which we need to answer, and so that we can proceed with our rasterization, make a rasterized line of this continuous vector defined line. However, this might look quite as an ugly line. Keep in mind that our pixels are super small, so we do not really see these lines in this edgy way, but we see them rather continuously. We want to secure through a line drawing technique, a line drawing approach, which is resulting in lines that are not too thick. They will be just as thin as possible, but at the same time, they should not form any holes. A neighborhood of a point is considered to have no holes if it will be connected to any of its neighbors. So for example, if I have this point, these are all its neighbors to which it can connect. Okay, so now we have so our essential question in drawing the next pixel from the left to right is whether the pixel will be, we know its x coordinate of the next pixel, but we do not know the y coordinate. We do not know whether the y coordinate is equal to the previous y or it is equal to y plus 1. So how can we find out whether we want to move and draw one pixel above a row, or we want to stay within the same row? The trick is that we evaluate our implicit line, which is described again here, but for a point which is xy 0.5. So this x is now, this is the x in the, so this will be the x coordinate here, x, and the y will be this level here. So this is xy. This point will be xy. Now we are adding xy 0.5. This is a point here, which is this point. You see, just between the centers of the two pixels. And now we are evaluating for this point, the functional evaluation. We know that it will most likely not be equal to 0, that it will not be on the line, but we evaluate whether it will be below or above. And this below or above depends on what value will this functional evaluation have. So we will put in these values x and y. So the y will be now y plus 0.5 for these values of our implicit equation, and we will evaluate the result. Now, for the evaluation, we will find out that if the value is smaller than 0, if the functional evaluation is smaller than 0, then our point, this point here between the two centers of the pixels, lies below the line. So in this particular case, which is drawn here, we will have functional evaluation which will be smaller than 0. It will be negative. And that means that our line goes above the pixel. If our functional evaluation would be positive, as it is in this case, then our point is above the line. You can simply check that by evaluating, for example, y with a very high value, which will be guaranteed above the line. And in this case, you will see that such a very high value will result in a positive number, because x1 is more than x0, so we will have a positive value coming from this term, and the higher the y, the more positive, the higher positive value it will have. So it will be a positive function if the point lies above the line. So if it's now the line is above the point, as it is in the first case, we will be drawing this pixel, and if it will be, the line will be below the point, we will be still staying in the same row. And this is a simple rasterization technique. And in each iteration from left to right, we know always what will be the next x coordinate, and we are evaluating whether the y coordinate will be the same or incremented by 1. Simple technique, and results into reasonable lines that are continuous and are having no holes. As you can already now see, a different rasterization of lines with slightly different orientations can be realized analogously, and sometimes they could be mapped to this case just by switching the 2 points P0 and P1. And by switching them, we will end up in this case. This is not the case in all cases, but in some, this will be the simple mapping to this simple case. This approach of rasterizing line can be also turned into an incremental method where not the entire functional evaluation of the line needs to be computed, but only a fraction of it. Keep in mind, again, that we have the following formulation for computing our point between one y center of the pixel and another y value of the center of the pixel. Between those two, where we are possibly in one of those going to draw the pixel. Now, if we are now adding, so please have a look at this formulation. We are adding x, but keeping y. So what is the difference to the previous evaluation, which we evaluated in the previous step? Well, it's just that here would be x plus 1 in this area, which means that we will have one more y0 minus 1 term. So we can simply add that, and then we will have actually the previous functional evaluation plus this term will give us the values for the new functional evaluation on with the y value at the same position. If we want to increase the position of the y, then we will not only increase the one more occurrence of the y0 minus y1 term, but also the term x1 minus x0, which is the term associated with the y variable. So here we have both terms, and this way we will be able to accumulate the functional evaluation and just have a few addition operations to be able to update the values. Of course, we can expect from already the compiler that the value of y0 minus y1 will be actually stored for us, and so that we do not need to compute it every time, or it will be available in the cache. And so is the case for the x1 minus x0 here. So this should give us an efficient evaluation of the line. However, such an incremental method would also mean that such a method is serial, sequential, and cannot be parallelized because the functional evaluation of the current step depends on the functional evaluation of the previous step. There is another issue which can potentially arise, and that is that adding several additions to a previous result, which has been already affected by the precision of the data structures which we are using, might lead to some accumulation of an error. So if we would like to have perfect lines, sometimes it might be necessary not to use the incremental method. However, for lines which are just few thousand points on the screen, this usually is not becoming an issue, and we should be able to have a performance gain of this sequential approach of this line drawing algorithm without any accumulation errors polluting our visual outcome. So after we have warmed up in the rasterization stage with rasterizing lines, let's have a look how we can possibly rasterize entire triangles, because those are the elements which are forming the surfaces in the 3D graphics. Well, we can rasterize the edges as lines, as we discussed before, but let's concentrate on how we can perform the rasterization of the triangles, and how can we interpolate the values inside the triangle based on the vertices. For that, we are using the barycentric coordinates, which we already introduced some time ago, and those will turn out to be very useful here, because we can, with barycentric coordinates, we can interpolate any value which is stored at the vertex, whether it is a color, normal value, or a texture coordinate. We can use the barycentric coordinates for interpolating these values over the triangle area. With the normal vectors, we have to be a little bit careful, because while the interpolation leads to an, in principle, normal vector with the correct direction, it will not be a unit vector, and therefore we will have to normalize it before we use it at a particular position. It is important to understand the rasterization of a triangle in a context of an entire mesh which contains these triangles. Such triangles are sharing the vertices and edges. They are not isolated, but one vertex belongs to several triangles, and the edge is normally shared with another triangle. Therefore, we need to be careful about how to draw these edges uh, between triangles because it might mm, not be obvious which triangle will be rasterized first. And based on the order of the triangle, the edge might be one time rasterized with the color of one triangle and another time with the color of another triangle which it's shared with. Therefore, it would be important to define a rasterization approach which is not rasterizing the edges based on which triangle comes first, but that there is some other meaningful rule. A good rule is that the triangle pixels are rasterized or belonging to a triangle only if their centers of the pixels are inside the triangle. If they still are intersecting the triangle, but the center of the pixel is outside the triangle, that pixel doesn't belong to the triangle. The convention is. We can still think of what happens if the pixel center is directly on the edge between the two triangles. While this is a case which rarely occurs, it might occur indeed, and therefore it would be important to make some decision. Maybe a decision could be to give it to a triangle which is closer to a particular off-screen coordinate. For example, a coordinate -1, as it was mentioned in the book. So the one triangle which is closer to this point would be the one which will be the considered to rasterize that um, that that the triangle will be rasterized on that position. The idea is that we are, for during rasterization, iterating through pixel centers, and we are calculating their barycentric coordinates. And based on the weights of these barycentric coordinates, alpha, beta, gamma, we blend the values, respective values from the vertices together to interpolate these. Here is a simple brute force approach how we could perform such a rasterization. It is not an efficient method, and we will be talking about a more efficient method just in a moment. But this one is clean from the perspective of the concept. So for all triangles, we will go through the entire screen through x and y coordinates, and we will compute for each pixel the alpha, beta, and gamma. And then we will evaluate whether the alpha, beta, and gamma belong to the range 0, 1. And they all need to belong into the range 0, 1, otherwise the point lies where? Outside the triangle. And once this is true, then the color, for example, in this case, can be blended together with the corresponding weights from alpha, beta, and gamma related to the individual vertices 0, 1, and 2 for that particular triangle. Once this color is interpolated, then we are simply drawing that pixel with at the position xy with the interpolated color. This approach is an unfortunate one, although it is clean, because it's very, very inefficient. Keep in mind that for each triangle we have been iterating through the entire screen, and this was absolutely not necessary. We have here another method which makes a very simple simplification of this, and that is that instead of traversing the entire screen, we will be traversing only those only such a sub area of the screen where the triangle can be possibly uh, be located. So for the vertices of the triangle, we are finding the x and y coordinates, the min and max coordinate for both x and y, which form as a rectangular area within the screen. And within this rectangular area of the screen, we will be then searching for the particular values of alpha, beta, gamma. And if these will be then bigger than 0, all of them, that means that that we are inside the triangle. Please note that in this case, we also have the alpha, beta, and gamma computed here, and it is computed based on the equation which we had already before, where we have the equation of the line, which is then normalized or scaled by the equation of a line with putting in the particular values of the point B, in this case for the beta. And here we have all these three barycentric coordinates calculated from these various lines. Hopefully you still remember the image where we explained this concept from the math lecture from a few days ago. So once all these three weights will be higher than 0, that means that the point is inside the triangle, and we will draw that point or pixel with the respective interpolated color. This approach can be also made faster through an optimization with an incremental approach. Keep in mind that if we have a certain line along which we will be performing the rasterization, certain row, for example, on the screen, then our increments of a particular value will be uniform from one pixel to another. So if we look at the evaluation of our function at a particular position, we can note that the increment of a particular value will be by the factor a in the x direction and by the factor b in the y direction, because those are those ones which are associated with the x, and then there will be one more a factor added to the already previously calculated functional value. So we can see it here on this example where we have various colors and we are interpolating the color, and we can see how the interpolation of the color is changing in each coordinate. While we are keeping the red channel constant, the green channel is interpolating, and from each pixel to another pixel, the increment is constant value. During the rasterization, it is important that we get rid of information which is outside the view volume and do not include that information in our rasterization process. The reason is the following. If we have a certain function, like maybe you remember in the viewing transformation, our function which was scaling the z, which was not so intuitive, but had the nice property that at the n near plane, the z was equal to n, and at the far plane, the z was equal to f, and it was having some order preserving behavior in between. Outside the range of n and f, it behaves not so nicely, especially the behavior of this function, which was presented, behaves counterintuitively, if a point will be located uh, behind the eye. While such situation might be rare, it might happen, similar to what we can see in this small illustration here. We have one triangle, ABC, and these are its world coordinates in the top view, and we can see that ABC will be um, their position of A and B is correct because their positions are within the um, within the view volume, and they might be moved a little bit, but in principle, they are the order is preserved of A and B. The problem is with the point C. With the function which we have just mentioned, the value of the point C will be changed dramatically, and it will suddenly, after the transform, the point C will be transformed after the far plane, and the orientation and the shape of the triangle will drastically change. Therefore, it is important that before we perform any rasterization, because in such a case, as we see here, the rasterization result will be entirely different. It is important that we perform clipping. So here, we only want to rasterize the part which is inside the view volume. So how such a clipping can be performed? It can be performed in in several spaces. It doesn't need to be in the world space. It can be in the camera space or eye space, as we used to call it. It can be also in the already perspectively distorted or scaled view volume. That is fine. And in all these uh, spaces, the clipping has to be performed. There are two approaches which are similar but not the same. One, removal of entities is called culling, and um, this removal has primarily the purpose of speeding up the computation. Culling means that we get rid of some geometric elements which we would waste time on computing, and they will not show up in our visualization anyways. Therefore, we want to cull them before we make an attempt to draw them. Clipping, on the other hand, is an approach where we are not so much concerned with the performance. Actually, treating the primitives and clipping them might be more time consuming than time winning. However, it will be concerned with the correctness of the result, as we have just seen on this small illustration on this slide. So we can clip the, the triangle in this case with the in-out test with 6 planes. If the test fails with or at least one plane, it means that the one vertex is out, or maybe several vertices, maybe 2 vertices could be out as well. So this is a simple test, and it could be based on the near and far plane, and it can be also based on non-parallel to each other planes, which are forming the view in frustum in the perspective projection case. As I said, it can be clipping can be realized in the world space, in the camera space, and it can be also done in the 4D transformed space without the homogeneous divide. How such a evaluation of the clipping can be done? Well, we can use the evaluation of our plane equations with a point, and if this equation results into value which indicates that the point is outside the the view volume, then this point needs to be clipped. When does it mean that it's outside? Well, this can be defined based on the sign on which side the, um, the the point will be inside. Our setup of the planes can be such that in case we have a positive value for all planes, this means that the point is inside. And if the point is defined for one plane equation as with a negative value, it could be outside. But it could be also the other way around, depending on the definition of the planes. Now, imagine that we have the success and we realize that we are clipping an edge between the vertices A and B, and there needs to be one of these two vertices, let's say the B vertex, is outside. Now, we would like to find out which is the point which is actually on this edge A and B, and it's actually also on the clipping plane. So, because that's the point from which we are going to clip the primitive. So, we have our description, parametric description of our line, and we simply put it into our implicit description of the plane, and by that we are calculating the parameter t. Once we calculate the parameter t, we calculate the position of the point, and based on whether this point is how many points from a triangle are outside and how many are inside, we will decide whether we need to compute another intersection with another edge and then perform the clip accordingly, or generate one or two triangles out of this clipped triangle, which we had to remove some part of it because of being outside. So now we approximately have an understanding of how the rasterization works, how does the clipping operates, and let's discuss a principle of such a 3D graphics pipeline. So let's discuss a small graphics pipeline which has a minimal amount of steps. So in the vertex processing stage, we would typically need to just not do much else than multiply all vertices with the compound model view transformation matrix. And that's all. After such pre-processing stage, our coordinates of our geometry of our objects or our points are in the screen coordinates and are ready for the rasterizer to do its job and generate fragments for all the geometry. After the rasterization is performed, the fragment processing can perform the hidden surface removal, meaning that the correct depth ordering should be realized. And with the simplest approach to that can be done with the painter's algorithm. The painter's algorithm operates on the primitives level, not on the fragment level. So a painter's algorithm would evaluate whether one triangle should be drawn over another triangle because it is closer to the viewpoint. So while this might work for several triangle constellations very well, sometimes the triangles might be um, done, positioned in such a way where it is difficult to define which triangle is before which one. This could be in a case, for example, when a triangle is uh, when a triangle is intersecting another triangle, as we can see it here. So which one is first? The choice would be arbitrary in this case. Even in the case if we have a non-intersecting triangles, but they are overlapping each other mutually, we might end up in a situation where it is difficult to decide, or there is no way to correctly decide which triangles is in front of which one, because each is partially occluding another one. Because of this, and because of simplicity of brute force approaches, a Z-buffer technique became very popular. A Z-buffer technique is simply uh, a screen coordinate grid which stores the closest depth for a particular pixel. So during the rasterization stage, each fragment, when it is evaluated, what is in terms of its depth is evaluated with the depth which is stored in the Z buffer. And if this depth, if the depth of the newly rasterized fragment is smaller than the one which is in the Z buffer, then this fragment will be written as output and the Z buffer will be updated with its depth. In the other case, when the Z buffer will have a smaller value than the Z value or depth value of the newly generated fragment, the fragment will be discarded because it will lie behind already another fragment which is closer to the viewing plane or the viewer. To, to work this correctly, we first, of course, need to initialize the Z buffer with a big maximal value, and then each element, each primitive, is being rasterized, and some of its pixels will be stored, and their color will be stored in the frame, so-called frame buffer, and their depth will be stored in the Z buffer, and some of them, other of them, which will be occluded, will be discarded. This technique is very popular and can be also parallelized, and therefore it has found its way to be implemented in the hardware graphics pipelines. However, the Z buffer is not a um, not a perfect solution in all cases. One needs to be aware of the potential issues associated with the Z buffer. Sometimes the Z buffer has not sufficient resolution, and in such a case, two different depths in the uh, so to say high resolution float coordinates might map to the same depth of the Z buffer. If the Z buffer an has an integer data type, then it might not have this fixed point representation might not have enough of resolution to store fine differences in depth. And therefore, sometimes one graphical element or geometric element might win over the position of another one, and in the next frame, it might be the other way around. And therefore, it is important to keep the precision of the Z buffer as high as possible, which can be achieved by first setting up the graphics pipeline in such a way which uses high resolution Z buffer. If this is not possible for some reason, or the high resolution is still not good enough, then we need to consider that the Z buffer is, or the its range is defined between the value near and far of the near and far plane. So the smaller the near and far plane distances, the higher the resolution of the Z buffer. We can see it here where we have the near and far plane, and we have the uh, the b different values which the Z buffer can differentiate. We will end up in a certain number of bins. We also need to take into account that this representation of the depth is scaled by this function, which we discussed on the viewing lecture last time, is non-linear. Therefore, which will lead to an actually favorable condition where closer to the camera, the bins are smaller, and the further away from the camera, the bins are becoming bigger. So this is useful because for close objects, we have a relatively high fidelity of the Z buffer, while for objects which are more far away, we have a more rougher resolution available. In this graphics pipeline, we have mentioned that one option is to perform the per vertex lighting. This means, or per vertex shading. This means that our illumination, as we learned, the von Blin or the Lambertian illumination can be calculated on the vertices only of our triangles, and then it can be interpolated throughout the the area of the object. We can see the result here. While this looks reasonable, one can say, we can also see that in these images we can immediately spot some visual artifacts which are showing up and actually are revealing the approximation of the sphere through the triangles. We can see how these triangles are sort of forming the surface of our sphere. So the per vertex shading is not the most fortunate choice. However, it is much cheaper calculation of shading because in case shading is a computationally demanding task, we perform it on a very low amount of elements, namely the vertices, which are orders of magnitude less than the pixels typically. And then we are simply rasterizing this. And as the rasterizer is an hardware implementation, we get this this performance, this calculation of the shading for all the pixels in some sense free of charge. However, the quality of such a shading is not very satisfactory in many cases, and also in some cases, especially in the interactive graphics, the interaction movement of the camera or the objects or the light sources will amplify these artifacts, these linear artifacts of the lighting caused by the Goro shading, as it is called, meaning the per vertex shading with interpolation of the colors. Therefore, these days, we would likely not perform such a calculation of illumination based on per vertex, but we will instead interpolate the normal of each primitive over each primitive, meaning that we calculate or we store the per vertex normals on each vertex of the triangle, and then these per vertex normals are being then interpolated over the entire area of the triangle. Then In order to function properly, we will need to scale them to become unit vectors, and then we are performing for each single pixel shading evaluation in the fragment shader. So not in the pre-rasterization stage, but in the post-rasterization stage, as we mentioned in the beginning. After this, we will have a reasonable representation of our scene. However, due to this discrete decision of whether a pixel should be drawn or not, we will often, unless we have a super high um, uh, resolution of our display, we will end up in some kind of edgy artifacts associated with the rasterization process. Therefore, it might be a good idea to, instead of using the, the discrete decision on whether a point belongs to a line or not, to calculate a certain fraction of a line passing through a possible pixel, and this fraction will be then associated with a certain shade of gray, so that our line will be so-called anti-aliased. So this edgy artifact is called aliasing effect, and anti-aliasing will get rid of this and provide us much more smooth lines. This might look ugly in such a magnification, but in case the lines will be on the screen, you will appreciate the anti-aliasing much more. Another strategy of performing anti-aliasing, which is implemented in the graphics hardware, is that the rasterization is performed on maybe 4 times higher area, so double the size of the screen in both X and Y direction, and then we essentially compute 4 samples um, per each. So we compute for such a large area our rasterization, and then we sample down or reduce the resolution of the screen and realize that we have computed 4 samples per each pixel in this lower resolution. And then, based on the value of the 4 pixels, we can decide whether we will be drawing a full ink color of the primitive, so to say, or just a fraction of its color. Finally, let's have a discussion on few strategies of culling. We have mentioned that culling is an approach to remove certain primitives from the graphics pipeline in order to gain performance. So there are several culling strategies which are interesting to consider. One strategy is a so-called view volume culling, where some elements, some primitives, or some objects are stored outside the view volume. And therefore, finding out that they are outside, maybe by some bounding geometry for simple calculation. If we find out that they are outside, we can remove them from consideration and not draw them and not send their primitives for rasterization or for transformation or for per fragment calculations. Another culling strategy is occlusion culling. This means we do have all the elements, primitives, the geometry within our view volume. However, some of the primitives will be occluded, and we can through various heuristics or other approaches, assess which elements will be occluded and which is not clear that they will be occluded. Once we know which elements will be occluded, we can again remove them from the drawing process. The last strategy, which is somehow the subcategory of the occlusion culling, is the backface culling. In case we have closed primitives, then we have some set of their triangles facing towards the camera and some set of these primitives facing the opposite direction than the camera. They will be not facing the camera because they will be behind. A simple dot product calculation between the uh, viewing or view direction and the normal vector of a triangle can give us, in such a case, a guideline whether the triangle is facing the camera or not. And such triangles can be then, which are not facing the camera, can be removed from the drawing pipeline. And by this, on average, we will save approximately 50% of drawing time, because in such a closed object, 50% will be of the triangles will be on average not facing the camera, and 50% will be facing the camera. So on this lecture, you have learned the alternative approach of rendering from to the image order rendering, the object order rendering, which is popular in various graphics pipelines, including the hardware implementations, which we are normally using when programming graphics for games or for other real-time applications. On the next lecture, we will look into details of a more fundamental topic, which is signal processing, where we will learn some underlying phenomena which cause aliasing or which cause proper strategies for sampling and reconstruction of a discrete signal. See you then. Bye.